Let me give you the quick recap of the last lecture. So we started radioactivity. So law of radioactivity is based on statistical physics, that is theory of probability. And what we saw that the fraction of molecule getting disintegrated per unit time is constant for the case when the number is the number n of the unstable nuclei is really large, very, very large. And this constant is called a disintegration constant. Also called decay constant. And symbolically, we represent by the symbol lambda. And therefore, we can write as dn by dt equals to lambda into n. So this is called probability. Per unit time. So lambda represents, what is the dimension of lambda? Time inverse, right?
Yes.
Yeah.
Because probability is dimensionless, it's just a number. It's a literal value. And per unit time is inverse of time. So that's why its dimension is time inverse. Now dn by dt, this term we call activity. And activity means it is also called disintegration per second. Which simply means how many nuclei will decay per unit time. And we can see clearly that activity is proportional to the number of live unstable nucleus. So this is the number of unstable nuclei yet to be disintegrated. So larger the number, more the activity. When n becomes really small, then activity decays exponentially to a very small value. And after some time, in fact, it doesn't follow the law of radioactivity. It will deviate from the prescribed law. But in our syllabus, we are not going to take that corner cases in which the variety is questionable. Rather, we assume that no matter what is the number, the validity is maintained throughout, and therefore we are able to apply the relation. All formulas can be derived easily. So, because minus dn by dt is lambda into n, so you can also integrate lambda dt, because lambda is constant, so you can integrate. So when you start the observation, you get some number, let's call n naught. And so you get the answer as minus ln n by n naught is lambda t. So t becomes how much? Inverse of lambda into ln n naught by n. So given the present live and the initial live nuclei, you can easily find the time is spent in the due process. And if you rearrange, you can also get n equals to, which is given the time relation and the initial number of unstable nuclei, you can find the remaining nuclei, which is yet to be disintegrated. So how many nuclei disintegrated in time t? Tell me how much. So you started with this much, now you have left with this much. So the difference is called the disintegrated nuclei, right?
Yes.
You can write as n naught e power minus lambda t. So the delta n equals to and delta n, because I'm writing the value by n. This is called the probability.
So delta n by n naught, right?
N naught. So delta n by n naught is the probability, because this is the total decay upon the actual number from beginning. This is the probability over the time t. And you can clearly see that if t tends to infinity, the probability tends to 1, which is logical also, because after infinite time, we will assume that all of the nuclei will disintegrate. So what is the probability of a disintegration of a nuclei in infinite time? So the answer is 100%, right?
100%. Yeah.
So the answer is 1. So you can see that a probability will grow with time. And if you plot the probability graph versus time graph, the one is upper limit, right? So one will act as the asymptotic, you can say, line. And you can also find the slope of the probability. See, I mean, what do you expect? The slope will be how much? dp by dt must give you what? So if you write dp by dt, what will get?
Lambda.
Dash 2 minus
Lambda e power minus lambda t, right?
Yes.
Okay. So this is the rate of probability, and at t equals to 0, what is the answer? So at t equals to 0, if you put a 0, you get the lambda, right? So This is the probability graph, and you can clearly see that at t equals to 0, the slope of the tangent will give you. So given in the question, if in a question, if they mention this theta naught, so we can directly tell the lambda from the graph as tan. Can we write like this?
Yeah.
So this is the lambda, and they may give you the graph, and they will expect that okay, you can figure it out from the graph itself. The answer. Okay. This was the asked in JEE Advanced a long time back. So you hardly see the probability question in the radioactivity, but this was the question of IIT-JEE Advanced when it was subjective. So it's very old question. So now the question is how we do the, finding the age of any object. So there is something called carbon dating. So how we find the carbon dating? So carbon will have two isotopes, C12 and
C14.
C14. So this is the stable one, this is unstable. Similarly, oxygen will have O16 or 18. Uranium will have how much? U35 and U38, right? So now these isotopes are found in some ratio in a given species. So if you have a tree, okay, a live tree, let's say we have a live tree. So now, no matter how the tree is, the nature has having some sort of design actually. So a live tree, because of the process of you can say photosynthesis, okay, and some other you can say activity, they maintain the ratio of these two. So this ratio is generally a very small fraction because the unstable is found in very small trace amount, and 12 is found in abundance because we know it's in abundance. A live tree will have a fixed ratio. So once a tree will die, okay, what will happen next? So once tree will die, the concentration, let's say we have some number N1 and N2 in the beginning. So let's say at t equals to 0, we have some number, call it N1, N2. So after some time t, what will happen? So some reaction will occur because once the tree will die, the process to maintain the ratio will, that will also die. The process, you won't be able to maintain the ratio. So after that, the 12 will start decaying into the 14 will start decaying into C12. Okay. So 14 will decay into. So which concentration will grow in value? 12 or 14?
12.
So 12 will grow in value and 14 will, 14 will decay in value, right? So what will happen that after MT, the N1 will decrease to a new value, N1 1 minus lambda t, right? This is the sorry. So what is the value left after some time t? What will happen to N2? Can you tell me N2 will happen? So N2 will get all the decayed values, isn't it? So N2 becomes N2 plus delta N1. You cannot get it. How many nuclei has decayed here? This is the live, the present
And
value.
1 minus e raised to minus delta, lambda delta.
So that many number of nuclei has become which nuclei? C12.
C12.
So can we say N2 will grow in value with time?
Yes.
N2 plus delta N1 is okay. So this is okay. So what is interesting here that the initial ratio and the ratio at time t becomes so generally you will be given the initial ratio as some number, so we can rewrite in some nicer way like this. So can we write this as look this carefully? So we can write like this, yes or no?
Yes.
Yeah, fine. So if they give you the initial ratio and if they give you the final ratio, can you find the time t? So let n1 by n2 at t equals to 0 is some number k, and at t equals to t, the let's call this as n1 dash upon n2 dash. So n1 dash upon n2 dash, that's given as k dash. We know the new ratio. So given the old ratio and the new ratio, can you find the time?
Yeah.
So so what we're getting, n1 dash by n2 dash is how much? Our answer was e power minus lambda t upon
Into by n1.
n2 by 1, right?
Yeah. So 1 minus 2.
Okay, this is given as k dash, I think so. And this you can write as 1 by k.
1 by k.
So let's multiply together. K dash by k plus k dash So now this is how we do the carbon dating. So for a carbon dating, what you need to know is the ratio of the two isotope in a live tree or in a dead tree. And by knowing the ratio in the live sample and the dead sample, we can estimate, we can have a rough estimate of the age. And because, and of course, you know that a tree may live for 100 years before it dies. So in context of 5,000 years, I think 100 years is nothing. So that kind of error we can ignore. Okay. So this is how we find the age of the tree using carbon dating. So for let's say if you have a rock with a trace of some radioactive isotopes. So maybe you have a ore of uranium. Which ore of uranium is famous? I am forgetting the name. Which ore? Tell me ore of huh?
Or acha, sir, no idea.
No idea. Ore of uranium is very famous. What is called? Tell me from Google. Google it. Some par, some sar, par, something. I don't remember. So which ore of uranium is famous? Search and tell me.
Which blend
pitch blend. Pitch blend, right?
Yes.
Have you searched it?
Yes.
Yeah, pitch blend, correct. So let's say if a rock is having a traces of pitch blend. Okay. So you want to know how old the rock is. Okay. So the rock, even the rock will have some formative years. Okay. So it is formed due to the either maybe different reason. It could be ignite rock. So the process is molten lava, right? Maybe some other process is also there. When the tectonic plates, collide each other, they take all the debris, from inside to outside, which takes the form of a mountain. So even rock will have a similar phenomenon of traces of a radioactive isotope, and these isotopes will again decay. So finding the ratio of the two isotopes of the same element, we can roughly estimate the age of the stone. Okay. So this is the one particular example I thought of giving you to understand that how the carbon dating is performed. Okay. Using law of radioactivity. Okay. So one thing is which is very common, which we call half-life. So half-life is the time in which the number of nuclei decays to half of its initial value. So after every half-life, what will happen? It will become half of the previous value. So after 1 T half, this is the answer n not by 2 power 1. After 2 T half, what is the answer?
Not by 2 square.
So after nth T half, the answer will be how much?
2 raised to n.
So this is the like amount decayed, and so the amount left is this much. This is the amount left, not decayed. This is the left. What is left, right? Number of unstable nuclei left after n T halves. The way you want to say it. So after n T half, how many nucleuses decayed? Number of nuclei decayed.
And not minus and not by 2.
Correct. So these are something really simple formulas. I mean, not a big deal. Mathematically, how we do? Because we have the formula n equals to n naught. So after first half, because this formula is since the beginning. So after 1 T half, n becomes half of the initial value. Correct? So this one implies what? N naught by 2 equals to n naught. So this will get cancelled. So you can write the famous formula e power lambda T half is ln 2 is 2. So lambda into T half is how much? And the value of ln2 you must remember. I hope you all remember. What is the ln2 value?
0.693.
0.693.
Yeah, 0.693. So it is logical that this will follow a hyperbolic graph. A greater lambda means it's smaller t half, logical, right? If you
Yes.
decay really fast, you will have less half life, right? So this is also a very nice parabolic relation. Lambda t half is constant equals to ln2. So if I plot the graph of t half and lambda, the graph is rectangular, have bola. So at any place, the product is constant. So if I know let's say if you plot the lambda and t half of various element, so knowing the t half of the given element, you can find the lambda of that decay rate and vice versa. So generally, lambda and t half are used alternatively, or you can say interchangeably, in expressing the equation of radioactivity. So you are not supposed to know both the answers. If you know lambda, it's fair enough. You will get the t half or vice versa. So in examination, they will not give you both. They'll give you either because they know that you can do the derivation from this simple relation. So t half. Oh. So lambda you can also write as how much? 0.693 by t. Okay. And if you go back somewhere here, so lambda itself is how much? T half ln2 by t half, right? So you can find the time of this time taken for decay is t half ln2 ln. Yeah, fine. And this we can further write in which term? Any guess? Ln y by ln x. I hope you know the relation. So t, since t equals to 1 by lambda, I'll just write it once again here. T equals to 1 by lambda ln n naught by n. And we just realized that this we can rewrite as what?
T half by ln.
Hmm?
T half by
So
ln.
it is ln2 by t half, right?
Yeah.
So what I was saying is that there is a property, I hope you all know. This we can write as log 2 n naught by n, isn't it?
Yes.
Okay, ln
Yes.
y by ln x is you can write as log of y
Y to
base
the base x.
base x. I hope you know. So this is very nice. And this is all our same way of writing, just like manipulation method. So t by t half is called number of t half n, and that's why you can write n equals to log of base 2 n naught by n, and therefore if you take the reverse process, you get the 2 power n equals to n turns out to be. So all are ways of writing. These all are ways of manipulating, and you're always free to do this manipulation. I hope this is known to you. That's why I'm just writing quickly. Any doubt in this?
No, sir.
Okay, all are same process. So this is like how to find the number of t halves. Divide the total time by t half, you will get the n, and then you can simply convert the relation using the property, and you will get the answer. All right, so we can move to the next concept. In radioactivity. So that's called the concept of parallel decay. So parallel decay means a single nuclei A will decay, but it will not decay into a single element, rather it will decay into two different elements. So because it's a large cluster of nuclei, so some of them will decay as B and some will decay as C. But the probability of both decay will be different. Let's say lambda 1 is the probability for the A to become B, and lambda 2 represents the probability of A becoming C. Okay, isn't it? Now, if you look at the parent, these are called the daughters. This is called A is called parent. So the daughters are coming from the same parent. So the initial concentration that we have to take for B or C decay will be N naught itself. But because the probability is different, okay, so we know that if some fraction of A will decay, then I can say decay of fraction of N, the fractional decay of N. This is the probability. So this probability must be equal to what? Can we write the probability? All are positive number, right?
Yes.
Because A is decaying, so that's why I put a minus sign. Mathematically, Dn is negative number, so minus will make it positive. So this is the probability, right? Or you can write this probability at any instant. So let me make it in general. I mean, not like this. So at any instant, it is left is only N. So this is the fractional decay of A. It will give you B. How many of you realize this part? Like, I'm writing the probability. So whatever the amount of A will decay, someone will become B and someone will become C, right? I can remove N also. You can think this way: the decay of A will result into the formation of B and formation of C.
Yeah.
Correct? Isn't it?
Yes, sir.
And from the activity relation, I mean, there are many ways of solving. So you can divide by time, you can get the activity relation. So activity of A equals to activity of B plus activity of C. And we know the formula of activity. What is the formula? So now we have to define something in lambda effective. So the effective activity of A, we can say lambda into N. And B is given to us, lambda 1 N and C. So N gets cancelled. So what you get? Lambda effective is how much? The effective decay will be sum of the decay, and that's logical only, right?
Yes, sir.
And that is why we can define the logical answer for this. So we can add lambda effective as ln2 by T effective. I'm writing T means T half. Capital T means T half. And lambda 1 you can write as ln2 by T1 and ln2 by. So this is called the, what is the effective T half of the parent if you know the T half of the daughters. So it follows the reduced ratio. So where T effective is what? Half-life of what?
Parent.
Parent. Now what is interesting that half-life is not equals to the half-life of daughters. It is rather inverse of half-life of parent is sum of the inverse of half-life of daughters. So here I have taken 2, you can extend for 3, 4, 5 or infinity. So it is like a reduced mass formula. In terms of lambda, it is very easy to understand that, okay, because it's an actual decay process. So the loss of nuclei by A is the gain by B and C. Okay, so that is an easy way to start with. So when you are in doubt, start with the count, just number, and then you can eventually calculate the. So T1, T2 are half lives of daughters. Okay. So we always see daughter, we did not say son, because the daughter may decay into something else, E and F. So it is not necessary that the daughter must be stable. Even the daughter nuclei produce maybe in the unstable state, which can further decay. And that is how the convention has been called daughter. So it's parent. So parallel decay formula is clear. How to derive the parallel decay formula?
Yes, sir.
In the parallel decay, what they will ask you? They will ask you mostly this question that given the half-life of daughters, what is the half-life of parents? So it's a inverse relation which you have to just add like this. You will get the answer. Any doubt in this? Tell me.
No,
No,
sir.
sir.
No, sir.
Yeah.
Is the half-life for a nucleus defined for a specific type of decay or overall?
For a parent, it is overall, right?
Like suppose if there's one mode of decay is alpha decay and you're getting one nucleus, and then beta decay gives you another.
let's say you go to any shop to buy samosa pav and bhajia pav. Your money will be lost in buying anything. So when your money will be half, when the your money will be half when the price paid is sum of the price, right?
Yes.
So it for you the money is important. So for every unstable nuclei, the count matters.
Okay.
So if A is becoming B, C, D, E, F, A is anyway losing, right?
Yeah.
So the total count will become half. Okay. So you can say the nuclei which you are forming B and C, we have given the probability at which rate B will form, at which rate C will form, lambda 1, lambda 2 are, that is the notion of lambda 1, lambda 2, right?
Yeah.
And okay, so the whole idea is it is the reverse process of calculation, that given the half-lives of daughters, can we find the half-life of the parent? The answer is yes. Okay.
So how is
Understood.
it half-life of daughter? Half-life of daughter, like that statement doesn't make sense. No?
Okay. It is like this. A forms B and C.
In B2 something.
Then B to something. D,
Yeah.
E, C to something, F, G. And you can keep on doing this. Okay. So even B will have a half-life, right?
Yes, but that will not be related to its own formation, right?
No, everything. See, if it is a, nuclei, then half-life means there are two ways of defining. It is like if you have some count right now, when your count will become double. Okay, that is like also half-life. You are becoming double. Let's say you are being generated instead of a decay only. So we'll come to that next question, in which there is a decay process and also production also. So that's called the breeder reactor. So we have something called breeder reactor. So in the breeder reactor, what we do is we generally enrich the uranium fuel rod. Okay. So in a way, you make more and more number of unstable nuclei through the moderate bombardment of the fuel rods with neutrons. Okay. So when neutrons will hit those material, it will be absorbed by the nuclei first, and the nucleus will go into the unstable state from where it will decay. Understood?
Yeah.
So you disturb the equilibrium and then decay will take place automatically. So let's say we have a reactor which produces certain element. Okay. So there is a manufacturer. And the rate of manufacturing of the radioactive nuclei is constant. So let's say you create any radioactive nuclei at a rate of alpha. So alpha is called the rate of production of radioactive nuclei Okay. So it is the dn by dt n produced. So how many nuclei you produce per second? Okay. Let's call the nuclei X, but the nuclei which you're producing is radioactive, so it will decay to some value Y, isn't it? So
Yes.
X will decay to Y by some process, I mean some radioactivity, and let's say the decay constant is lambda. Okay. Decay constant is lambda. So in the very beginning, what will happen? In the very beginning, the number of X is 0. Let's say you just switch on your machinery which will produce the X. At t equals to 0, how many X we have? Tell me.
0.
0. So at t equals to 0, we have 0. So that time there is no radioactivity, but as I have said, that the law of radioactivity is a statistical phenomena, and it's defined only when n is large. So let's say after some time, you have really produced a large number of nuclei, and then you can expect the law of radioactivity to be applicable. So let's say if I write at t equals to 0, now this 0 is the 0 for applying the law of radioactivity, not actual 0. Okay. So let's say after some time, maybe after 1 second, it has produced enough nuclei to allow you to apply the law of radioactivity. So 1 second is good enough because the production is 1 curie. What is 1 curie? How much is 1 curie? I think 3 into 10 power 7 DPS. Just check the value. I don't remember the value. 1 curie is how much? I think 3.7 10 power 10. I think 3.7 10 power 10. Anyone please confirm? How much is 1 curie?
Yes, sir, it is
Yes,
correct.
3.7.
0.7.
In 10 power 10, right? Okay.
Yes.
Yes.
Yeah, I remember 3.7 something. Anyway. So 1 curie is this much DPS. So in 1 second, you have 10 power 10 nuclei. So I think few seconds are sufficient, isn't it? So the production rate is very far, I mean, very high in terms of count, and very soon the law of radioactivity can be enforced in a situation. So at t equals to 0, let's say we have this is n, this is 0. So what is the rate of production? This is the rate of production, the net, not rate, the net rate of production. Net rate of production. Why I'm saying writing net? Because here we have production and then decay. Now decay will grow with time, isn't it? Because if you remember the activity relation, you know activity is lambda
Yes.
n. So unless we don't have n, the activity is roughly negligible, isn't it? So can we say that in the very beginning, alpha is much bigger than a?
Yes.
At t tends to 0, when you are in the very initial condition, because the nucleus has not produced, so the activity, we cannot imagine any activity. So production is the only activity, isn't it?
Yeah.
Production is the only activity. I mean, activity means production is the only event happening. The activity will begin once you have the sufficiently large number of n, because lambda is a very small number, isn't it? Lambda is very small number. Do you realize this? You may not. To give you a rough estimate, the the half-life of carbon is how much roughly? I think 1508 years. How much? What is the half-life of carbon? It is in thousands of years, I think. Just check. Some facts and figures you should know actually. How much is T half of carbon? Just let me know.
5730.
5730 plus
Yeah,
minus
so roughly
40.
I said 5800 kilo, sorry, 5800 years, right?
Yeah.
Roughly, right? And what is the half-life of uranium-235? Just check. Or 238, just check which one is answer.
So 235,703.8 million years.
Hmm.
And 238 is 4.47 billion years.
Oh my God. So because that's very stable. So I think the 235 is more unstable, isn't it?
Yeah.
All right. So you can imagine that for all practical purpose, the life on the earth is nothing compared to the half-life of these radioactive elements. Now, what you need to understand that this is very large. If you convert into second, you can understand how small is that. So lambda is really small. So for activity to be anyway significant, the n must be very large. Yes or no?
Yes.
So can we say without any doubt that alpha is much bigger number in the beginning?
Yeah.
So what is the net rate of production? So we can say the net rate of production is the production minus decay the activity. So let's say you have produced n nuclei. So at what rate you are going to decay? Lambda n. And without the loss of generality, can we assume the lambda n is less than alpha? See, this part is radioactivity. This part is not. This part is like we are writing the equation. How many are getting this idea? What I'm saying? dN by dt, the rate of production. So the net rate of production is how much? I'm producing at alpha rate. I'm losing at lambda n rate. Correct?
Yes.
Yes,
So
sir.
can we write the net rate of production is this much?
Yes.
But there is something interesting here. As n will grow, because you're saying that net rate of production. So can we assume that n will keep on growing? Although there's a decay, but alpha is dominating factor. So the count will eventually increase. Yes or no?
Yes.
Yes.
But if the count will increase, the activity will also become more and more as time will progress. Yes or no?
Yeah.
Yes.
So if alpha remains constant and activity will keep on growing, so a time will come when the production and decay will become
Equal.
Equal.
that is called radioactive equilibrium. Okay. So at a radioactive equilibrium, what happens? The rate of production and the decay rate both becomes. So what is the maximum count we can get in this reactor? So at equilibrium, the dN by dt becomes
The net reaction becomes 0.
0, because see the rate of production and rate of decay both are matching now. And that will happen for sure because the activity will keep on growing forever. As you keep on growing the n number, the activity will not stop. So dN by dt is alpha minus lambda n. So the first question is called for radioactive equilibrium. This is called something, I think some better name is that radioactive equilibrium or something better. I'm just anyway, as of now, I'm going to say this is. So for a radioactive equilibrium, can we say dN by dt equals to 0?
Yes.
So alpha minus lambda, this is called the n final. So how many maximum number of nuclei we can have eventually in such a reactor? The answer is alpha by lambda. So this could be a potential question in the examination. Okay.
Yes.
Any doubt in this, guys? So this is the breeder reactor in which we have the production of the nuclei, and because you do not have the control over the nuclei, so you try to keep lambda. See, if you know the final, let's say to carry out certain project, you need n final to be certain value. So you need to know that what alpha I must choose in the beginning to achieve that task, because lambda is anyway predefined, isn't it? So for a given isotope, the lambda is predefined. It is known to the world. And there is no control over lambda. Can we control lambda?
No.
No. We cannot control lambda. So let's say if a certain kind of nuclear fusion or whatever reaction, you know that you need to have that many n values. So alpha is chosen in such a way to get the alpha by lambda to the desired value. This is how it is done actually in the nuclear power plant. Okay. So they use this, these all are called the breeder reactors to achieve the task. Depends on how many kilowatt of energy you want to, create and so on. Okay, so moving forward, this is the one type of question you will come across. The dn by dt we got is alpha minus lambda n. This is a simple differential equation which all can integrate, and you can tell me. So when t is 0, what is n? Okay, don't know, n is n. This is n. So can we write the n as a function of time t? So this will be a formula, isn't it?
Yes.
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 You can clearly see that when t, if you put t equals to 0, n is 0.
No.
Okay, I know there's some of you are getting stuck in the integration, right? So you all know integration, I hope so.
Yes.
Yes, sir.
Do you want me to explain the integration part? Anyone? If you find the itself part, I'll explain.
No, sir.
So if you can clearly see, as t will be 0, n will be 0. And as you put t tends to infinity, you can clearly see the n is alpha by lambda, right? And that is exactly the case of a radioactive equilibrium. So theoretically, we say that after infinite time, it will achieve the equilibrium. I mean, infinite time is a way of saying it. Okay, infinite means what? That t is much bigger than lambda, t half. So if t is, let's say, 10 times the t half, you can assume t as infinity, right? So what is the meaning of t tends to infinity? It is very simple. T by t half, I mean, is more than 10, much more. So it is good enough to call it as infinite time. Okay, ji? So this is called the production and disintegration taken together. So the last concept is called successive disintegration. So what is this disintegration? Let's say there is a king, very bad example, but anyway. So this example I'm doing for many years. So I'll continue with the same example. Although it's very bad in today's context. So let's say there's a king who is very sick. Sick means physically sick, not well. and he is blessed with a boy. No gender influence, just I'm taking this old example. Nothing to do with the patriarchy. So there is a king who is very sick and he gives birth to, blessed with a baby boy. And the day the boy was born, the king died. So what will happen? All of this, the kingdom, the property, and the ownership will be given to the whom?
The kid.
The boy. The new, like the Mahendra Bahubali, if you remember that movie, there's a movie, Bahubali. So that boy is born and everything that his father had given to the son in no time. So for this event, can I say the half-life of parent is almost 0?
Yes.
Because the parent was there and now he's no more there. And all of the number of, you can say, all of the nuclei of that parent has become the nuclei of child. So this is the case called in which parent will have very, very small t-half, very, very small t-half compared to the t-half of child. This is the case. How many of you realize this? That the day parent, you see the parent and you don't see the parent. So parent is totally consumed into daughters, right?
Yes.
A parent
Yes.
is completely consumed to daughter in no time. So if it is happening such a at fast rate, can we say the parent is having very poor t-half? I mean, there is no life.
Yeah.
So what is t-half? Understood? Half-life, don't say half-life, there is no life. So t-half is 0, isn't it? So
Yes.
this case is called when lambda parent is much bigger than lambda daughter. Do you realize this fact, this condition?
Yes.
Case 1. So all of the money is now available to what? The child. Oh, you can see the daughter nuclei. And then daughter will spend as per its own lambda, isn't it? So this case is
Yes.
interesting. A decays to B.
Yeah.
And B is also unstable. So B also decays to C. So for C, B becomes the parent. Understood?
Yes.
And lambda A is the decay constant of A, and lambda B is the decay constant of B. C is the stable one. We have to assume. Otherwise, life will be like really hell. And here, what is the condition? The lambda is, I'm taking the case 1. We'll solve one by one. Case 1. I'm assuming that lambda is much, much bigger than lambda B. So A is in really hurry. Okay, I don't want to live further. You just take all my money and just spend as per your decay constant. Okay. Your ability, you can say. So if I think this way, if I say t equals to 0, this is n naught, and B is 0, C is 0. At t tends to 0 plus, can you guess what will happen?
And not will be.
A becomes 0. B is unknown.
See, it is 0 plus. The day you are born, it's over. Do you realize this? What I'm writing here?
Yes, sir.
Yes, sir.
And then at any time t, it is simple.
And not.
Yeah.
Yeah.
Am I right? Let's
Yes.
check. Tell me if you have understood this part.
Yes, sir.
Yes, sir.
So in this case, there is no question of a radioactive equilibrium, isn't it? In this case, there is no question of a radioactive equilibrium of B, because B is getting everything in the very beginning. So the production of B has stopped in the very beginning only, right?
Yes.
The only thing is decay. Okay. So the king has died, and somehow the B will do whatever it wants to. And after time T, B will be left with this number of nuclei. And the decayed part of B is the formed part of C, isn't it? Hello, hello. Hello.
Yes, sir.
Sir, the second part refers to B and the
Yeah.
second column refers to B and the third column refers to C, sir.
Correct, correct, correct.
Sir, that means shouldn't it be the opposite?
No, the B will decay to produce C.
Yes, sir.
So B, so after, see, you have these many numbers. How many numbers are left after time T?
Okay, sir.
And the difference will be the number of nuclei produced in C, isn't it?
Yes, sir.
So here can be right for this case, NB equals to N naught e power minus lambda bt, and NC
Yes.
equals to N naught 1 minus e power minus lambda bt.
Yes, sir.
Okay. I hope this is clear to all of you. The case one part.
Yes, sir.
Now the case two. Case two. Is spoiled brat. You must have heard this phrase. So you know this phrase? The king,
Yes, sir.
the king knew that my son will not value the money. He was very much sure. Because the B is, the lambda B is more than lambda A. You give 100 rupees, he will spend in no time. So how to control? Don't give much. Give as it takes. So the ability to consume the nuclei for B is faster compared to the ability to consume A. I mean, the A is consuming that rate, right? But we should also know that your ability is more, but your wealth is less. So right now, who is having all the wealth?
A.
A.
B is now having nothing. So at T equals to 0, so daughter having decay constant much bigger than father, I mean parent. Don't take daughter as any gender, it's just a symbolic notation as per the convenience in physics. So daughter and parent is just an understanding. So A is parent, B is daughter, B is parent, C is daughter. And C is a stable daughter. So C will have no gender. Okay. So now tell me, if B is consuming at faster rate, but the B is having nothing in the beginning, right? In the beginning, whatever you have is at T equals to 0, we have N naught, we have nothing, we have nothing. Isn't it?
Yes, sir.
This is the case. Now, after time T, some of the nuclei that A will produce will become B.
Yes, sir.
But as the B is getting the nuclei, it will not hold it. It will also decay into C, right?
Yes.
And in fact, it will decay at faster rate. So there is a problem. We do not know how many number B will have exactly. Do we know?
No.
No, we don't know. Okay, we know one thing about A. Because the A decay is known to us, isn't it? So A is simply decaying. So what is the value of A? N naught e power minus lambda
Minus
AT.
IIT.
The problem with B is behaving as a breeder reactor. It is getting produced by A. So A is the parent producing B, and B itself is decaying. So it will follow exactly the previous to previous question, alpha question. Do you remember the alpha question? The alpha question, do you remember?
Yes.
What is the basic difference between the alpha problem and this problem? in the alpha problem, the rate of production was constant. But here, what
Yes.
is happening? Is the rate of production of B is constant?
No.
That is the problem. The rate of production B is not known to us. Understood?
Yes, sir.
Yes.
That's the biggest issue actually. So the problem is the rate of production B is, not constant, and decay is anyway variable. So now you need to understand that how to write the equation for B. A is easy to write, so I can just name it NA for the sake of writing. But I cannot say any value of B. I can just assume some variable NB and some variable NC. I have no idea how to write all this. So what is the rate of production of B? The net rate of production of B is how much? Any guess? It is getting produced by whom?
Minus DNA by dt plus.
What
Plus
is alpha? What is
plus
alpha?
DNC by dt.
What is alpha here? The decay of A is the alpha.
Yes.
So activity of A is alpha. Do you realize this?
Yeah.
So can we say lambda A N A is alpha? At a given instant, the count of A will decide the alpha of that instant. Yes or no?
Yes. Yes.
Yes, sir.
How many of you realize this? That the decay of A depends on the instantaneous value of Na,
Yes, sir.
Yes, sir.
and that will act as the rate of production of B, like alpha of B, isn't it?
Yeah.
But B is not very, calm. B is also going to decay. So if the count of B is NB, it will decay by the rate lambda B NB, yes or no?
Yeah.
So this is your actual equation. This is important equation for you. So for B, this is the differential equation we need to solve. But before we solve this equation, now there is an interesting fact here. Can we achieve the radioactive equilibrium here?
No.
No. Definitely, yes, we can achieve. Because A is producing at a rate and B is spending at a rate, and B can spend more than what you can give, right?
Yes, sir.
But the initial number of A is high, very high, and B is very less. So a time will come when the rate at which A will give, see, lambda is small, but N is bigger, right?
Yes.
So lambda into N can be equal, no? Eventually.
Okay.
Isn't it? And this equation is streaming out of this formula that, okay, yeah, I can be 0. So dNB by dt can be 0, yes or no?
Yes.
So in this case, you can actually achieve the radioactive equilibrium, isn't it? So B, you means B can achieve. Tell me guys, B can achieve radioactive equilibrium, yes or no?
Yes, sir.
So the question will come to you, for B to achieve the radioactive equilibrium, what will be the relationship between lambda B and lambda A? In fact, I have written that answer there. The B should have the greater lambda. The daughter must be having bigger lambda than the lambda of parent, isn't it? Think about it. Tell me.
Yeah.
Okay. And see, lambda, in fact, lambda B is much bigger than A. So it's like the A is very frugal. It doesn't spend any money. So it will give you only per day 1 rupee coin to, go and buy some, what comes in 1 rupee? I don't know. Maybe some toffee. So although he's a king, but he doesn't give even a single penny to the kids. Okay, maybe the Mukesh Ambani. What possible?
Sir, I didn't understand how the condition was derived from the equation.
Condition not from equation. Condition is already there. Then we got this
Acha,
equation. I'm okay. We will derive the condition later on when we have the actual equation.
Okay.
So for radioactive equilibrium, what we got? The B must have bigger decay constant than A. Yes or no?
Yes, sir, that only I'm not sure how you got that. That we need lambda b to be greater than lambda f for equilibrium.
Because initially the count of N is very large. B is almost 0.
Yes.
So after some time it will reduce and it will grow. Let's say my count is still very big. So lambda is small lambda into big N can be equals to
Big lambda.
big lambda into small n.
Okay.
So when these two will become equal, then the count of B will be constant in that instant.
Samda.
So I'm saying that a radioactive equilibrium can be achieved.
Got it.
And also because that T half is in million and billion of years, as you said. So for a few years, we can say the equilibrium will be maintained. So over the years, it can be maintained, if not for billion years, isn't it?
Yes.
Not for billion, but I can say for a few hundred years, it can maintain the radioactive equilibrium. Yes or no?
Yes.
Eventually, it will surpass, but who talks about it eventually? It's like a big life, and we are living a small life on Earth. I have always discussed that compared to the cosmic time scale, we only exist for dt, isn't it?
Yes, sir.
And in that dt, we are talking about all this equilibrium. That's too much of dt. Understood? So now the question is how to solve this equation. And probably you can solve it. So d and b by dt, because see, c we cannot determine unless we don't know b. Okay. Because c is only because of the decay of b, isn't it?
Yes.
So as of now, you know only one answer, NA, right?
Yeah.
Nothing else. So this is how we are going to solve. So dn b by dt is how much? Lambda a into n naught into e power minus lambda a t minus lambda b n b. So you can rearrange. And this is some very famous differential equation from mathematics. Okay. And then we can write it as dn b equals to plus lambda b nb dt equals to lambda a n naught e power minus lambda a. Okay. So what else we can do here? We can multiply both sides with lambda bt. So multiplying. Okay, if you know mathematics, you can solve from there, but anyway, I can do it this way. So multiplying both sides with respect to e power lambda bt. What will you get? You get something really interesting. dnb into e power lambda bt plus lambda bnb e power lambda bt dt equals to lambda a n naught e power minus lambda a t lambda b. Oh, lambda b is bigger, right? Anyway, so you know how to write this.
ET.
But this is really interesting. You know what is this? This is the d of nb e power lambda b. The entire time. use the product rule, we get the same answer. Can you check?
Just getting
Yes.
it.
So this is so easy, right? And now I think
DT.
now I think this is completely integrable, right? Isn't it? Because I know that at t equals to 0, the NB term was 0. So it will become the same term. So d of something is something. And in the beginning, it is 0 only. So the LHS becomes the same. So I can just ignore the limit. But on the right hand side, we can add 0 to t. So after integration, what are we getting? NB e power lambda bt equals to, we got something really nice. Lambda a n naught upon lambda b minus lambda a into 1 minus e power. I think this is the answer, right? Okay.
Yeah.
So what is NV finally? We got NV with all the effort. And this is the answer of NB, yes or no?
Yeah.
Okay. So you can see something you can derive from here. So if okay, this is the in general answer, now I can get the first answer using this relation. The first answer which I got without doing this. So if okay, now I will take this. Let's say if I say the lambda b is much bigger than lambda a. Okay. So e power lambda b is also much bigger than e power lambda a, yes or no?
Yeah.
So e power minus lambda b is much less than e power minus lambda a.
Yeah.
And if lambda is much bigger than lambda a, then NB can be written as lambda a n naught upon lambda b minus 0, or like compared to lambda b, a can be ignored.
Great.
And not only this, the term here, because e power lambda bt is very, very small. So what we get? This term left. Lambda is b is much bigger. So it is again a very small number. Okay, let me check. B minus fine. Lambda. No. What I'm missing here? If lambda b is much bigger than lambda a, lambda 80. Something we are missing, something is missing. Can you just check the value where I have missed something? lambda b NB equal lambda b dt. And then this is then, okay. So the mistake is this is correct. If you recall it, we should have written this term first, right? So you get this answer. So NB into e power lambda dt. And it's, this is 0, this is 0. Correct. That is 0, that is 0. So this term should get cancelled. So this we can ignore. So this now we have f with e power minus lambda at t. But this term is remaining. I mean lambda a lambda b should cancel out. So something I have missed. What I have missed? Lambda. Aha. Lambda a is much bigger than the first case was what? The parent was having high value. I think something I made a mistake. Yes, no, this is correct now. Let me just change this. Oh, everything is correct. So what was the case one? Case one was when if the lambda a is much bigger than lambda b, right? When the decay rate of a is very fast. So in that case, what we get the answer? NB equals to lambda a naught, because a is much bigger than b. A is much bigger than b. So then what you can get? Minus lambda a.
Yes.
And what we left with? Right? Okay, I think this sign I haven't changed. So this term will be okay. Anyway, we have to write like this, which you can write as this some manipulation. We have to change this, the order of writing. So now we can get the answer, right? Yeah. All right, so you can see the NB will have the formula which we were expecting, right?
Yes.
So in the first case, this is what we were expecting, isn't it? And we got the same answer. And because now you know the NB, can you find the NC? So what is NC? So dNC by dt equals to lambda BNB, isn't it? The activity of B is the rate of production of C.
Yes.
So in general, the dNC by dt will be how much? It will be lambda A lambda B upon lambda B minus lambda A into e power minus lambda AT minus lambda BT upon minus time writing properly this way. And therefore, this is a term The D and C turns out to be lambda A lambda B upon lambda B minus lambda A into e power minus lambda A T minus lambda B T dt integration 0 to T. So what is the answer coming? Tell me. So this is how much coming? Tell me, guys. NC equals to minus 9. Just check. I mean, I don't know whether this is correct or right. Something like this will come.
Yeah.
Yes, sir. It's correct.
But okay, no one is going to ask you the lambda C value for sure. Okay. Now, what they will ask you? Let me tell you what they will ask you. In JEE mains level, what you can expect? None of these relations are required. You just need to know this relation. And you can write it here directly for radioactive equilibrium. For radioactive equilibrium, what you can write? dNB by dt equals to 0. This implies the activity of A equals to activity of B. That's it. So you can expect some formula, I mean, some question based on this relation. That's it. Beyond this, if you know mathematics, you can solve. So this is called like a integration. Is it homogeneous? Non-homogeneous. Anyway. So you have to practice this and just remember the process of deriving differential equation and get the answer. What is left? I think we're done with the radioactivity. I think. Hopefully. So we can do some numerical and then we can also start the semiconductor today. Okay, guys.
Yes, sir.
So 1 or 2 questions, then I'll start the semiconductor. So let's do the PYQs. Anyone having PYQs right now? I have shared
Yes.
the one PDF today itself. You can open the chapter nuclei chapter, atoms and nuclei. Just see the radioactivity and check the question. Let me also see first. Can you see the chapter? Which page is this? I don't know. Tell me the page number. Nuclear, yeah. Page number, I think the PDF is 469. Okay. So the first question you can solve without reading, without solving, isn't it? Because you are supposed to know the answer. 10 power. So what is the density of nucleus? Are you guys on the same page?
Sir, which page?
469 of PDF.
Just
Yeah. If you look at the PDF, you can see 469. Page number. 469. Okay, let's go to the. Yeah, you can just see the first question. That's easy. But anyway, let's do the radioactivity. So question number 28 onwards. Topic 3, radioactivity 471. Can you go to page 471?
Yes, sir.
Yes, sir.
Like that is the scrolling page. I think the number of pages is 463. The printed part. P463. Are you there on the page?
Yes.
Yes, sir.
You can see the topic 3, radioactivity.
Yes.
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 And you can try whatever you want. Yeah. So start with some random question. The first question. So there is the graph of activity versus time. Okay. And their T half. So log of activity. So whenever you have a graphical problem, what you do? First of all, you find the relation. Okay. So hopefully you'll get the answer from the slope and something. So we have the formula. What is the activity formula? Tell me, guys. A equals to. Okay, it's written R here. Lambda n, correct?
Yeah.
And we know this we can rewrite as a lambda n naught e power minus lambda t.
Yes.
So ln R is how much? Constant. So ln lambda n naught minus lambda t. Isn't it?
Yes.
So y equals to mx plus c.
C.
So what is m here?
Minus lambda.
Okay. So now you know this. The more the lambda, more the slope, the value was steepness,
Yes.
and more the lambda, lesser the half, t half, right? So
Yeah.
you're not supposed to guess the answer, just to get the equation and you can correlate the answer. So what should be the right answer? Tell me. Just check the steepness, you will get the answer. So which graph is the steepest? I think B is the steepest, right? So
B.
B will have
Yeah.
maximum lambda, minimum t half. Huh?
Yes.
So B will have minimum t half. Then A and then C, right?
Yes.
So B, then more than B will be A and C is maximum. And you can just tell me which answer is correct.
C.
So in actual examination, if this question will come, can we expect this to you can solve in 30 seconds?
Yeah.
In graphical question, I have seen that many students they try to find the answer in the graph. Okay, no. A graph means you just look at the y and x, try to derive your equation in those terms, and then solve it. Don't play with the just random trick. Okay, 29th question. Can you see? A radioactive nuclide decays by two different processes, which means the parent can decay by two different ways.
Yeah.
And the half-life of daughters are given.
Yes.
So what is the half-life of parent? T1, T2 by T inverse T2?
Yeah.
1000 by 110. How much? Roughly how much? 1000 by 110. Roughly 9 seconds.
Yes.
Tell me guys, yes or no. Everyone. Are you guys getting this?
Yes.
We are just solving mentally. I mean, there is no need to apply brain. If you're not able to solve this, meaning like it's difficult. If you want to solve more questions in JEE-Mains, you have to be very fast. Question number 30. 29 is done. Any doubt in that? Anyone tell me?
No.
Okay,
No.
30. In a radioactive material, fraction of active material remaining after time t is 9/16. The fraction that was remaining after t/2 is how much? Tell me. So t/2 means what?
Half-life.
Half-life. No, it is simply given t, not t half.
Okay. Okay.
So just use the formula. So the fraction of active material remaining after time t is this much. What is the active material? How we calculate? The formula. See, you are not supposed to do it blindly. Just play with the formula. It's very easy. It's like you have to take the square root answer. I know I can square root 3/4. But
3 by
anyway, how
4.
to solve? Correct. So n equals to n naught e power. So this is how much given. So what is n
Nine.
dash? Correct?
We can take a ratio.
We can take the ratio. So this is nothing but the lambda t/2 whole square, isn't it? Understood? Because in power gets multiplied in case of, I hope you remember this. So n n dash is how much? N naught into under root of n by n naught, isn't it? What am I writing? Okay, you can take the ratio. But you can take the ratio after squaring only. No? This is correct. So given that, yeah. So if they're asking any fraction, they're asking fraction only. So n dash is how much? N naught into e power lambda t/2. What is e power lambda t/2? Am I right, guys?
Yeah.
So what is n dash by n naught? N by n naught. That's it. Yeah, anyway, this is something you all can do. 31. All are manipulation. Just you can do it as fast as possible. Please solve all questions. We will practice enough not to solve again. This is okay, na? This is okay, na? Any doubt in this? Tell me.
No, sir. No, sir.
So just know how to manipulate. That's it. So these questions can be actually solved in 1 minute. Less also. Just try to understand the process. So today we can utilize the time for semiconductor. We can study in slightly more detail because more time is more detail. So probably I'll keep lectures this week also. One or two lecture. Except on holidays. So 25th I will not keep lecture. You can go to church and pray. Next is done. One is over. What is that? The activity of a sample falls from this to this. So you know the formula of activity? Time is given that the half-life is close to. Yeah, you can do this. How fast you can do this? And you don't have to use calculator in examination. So you have to think, okay, how to do this calculation. So although it's easy, but so anyone getting the answer?
Trying it, sir.
Both fast. I'll give 1 more minute. See, the relation of activity and the n formula both are same, right?
Yeah.
So the half-life is close to. Do you remember the formula? I have given you formula. The T relation. T is
Yes.
close to.
Yes, sir. 1 by lambda ln.
T half by ln2
Yes.
Okay,
into
that.
log 2. Understood?
Yes.
N not by n.
This
So
will
you
be
can address
by 8.
700 by like this, no?
Yeah.
Yes.
So this is how much? 1 point?
1.4.
1.4. 2 power something is 1.4, right? Okay, anyway. So this is okay. This is given 30 minutes. So 30 into ln2 by log of 2, 1.4, right?
Yeah.
So this is 0.7 roughly, 0.693. And 2 power something is 1. This is roughly 1. Close to 1, less than 1 actually. So because this is less than 1 answer, this is how much? More than 21 minutes, slightly.
Yes, sir.
Yes.
No. 20 minutes. Half-life is this only, no? I don't know. How much was that? Was it log 2 only? Log 2. I don't know. My bad. This is not there. Only this much, right? Log 2 we have taken log 2. T half into log 2, right? So T half into log 2. Understood?
Yeah.
That's why I was saying this is not correct. So this is how much? ln2 will not come for sure. But less than 30. So more than 30 this is the answer. More than 30 is log.
Sir, log 7 by 5 is 0.85 minus 0.7, which is equal to 0.15.
Yeah.
And then log 2 is 0.3, so it would be t half by 2.
You have a 2.
Yes, sir.
Yes. So activity goes from, okay, just a minute, the question is given. Where is the question? The activity of a radioactive sample falls from 700 to 500 in 30 minutes, right? So T is how much? T half. Oh, T half. Oh, sorry, my bad. This is 30. T half we have to find ln. So log 2 of 705. So we can write as T half equals to, yeah, fine. So log 27 log 25, right? So this is roughly how much? 3. Roughly 2. Roughly 1. No, this is not good. Values are given or what? No, nothing is given. But it is going to be more than 2 for sure, more than 30 for sure. So log 7 is how much?
Sir, I'm getting approx 60.
60. Yeah, so that's correct answer. That should be
yes,
the correct answer.
Sir, I got 65, about 65.
Oh my god. So that's very confusing. After getting 65, then
Yeah, but the answer
66.
is 66, it's 62.
Yeah, so that's close value. So log 27 is how much?
Sir, 1/2 sum, that denominator value.
Okay, this is 1/2. Log 2 1.4, log 2 1.4. The 2 power, okay. Oh, that's fine. This is exactly right. This is the root 2, no? Root 2 is how much? 1.414. That's what they have given the value. Okay, that's nice. So this we can attach log 2 per half. The answer is 60. So this is the next answer is 62 is the right answer. Very good. So the manipulation is also important. Otherwise, it's difficult. Yeah, it is 1.4, so it is always root 2. Correct? So remember these values also. Like in doing calculation, you have to be very careful that if it is 1.73, you know it's root 3. Next. Solve 32. I hope the calculation is clear.
Yes, sir.
32. I think this is just formula based, right? Substituting, look at the answer. Anyway, just do it for the sake of doing.
Done. Sir.
Then no? Keep on doing next. I think some good questions should come. Okay. Okay. Anyway, solve 34. just to make a change. And for question like 34, you're not supposed to even know basic physics. Just know what is alpha, what is beta particle, and you can get the answer. So 6 alpha and 4 beta. You know the answer?
Yes, sir.
I think this is simple. No?
C.
See. So the mass number will be affected by how much? 24.
Yeah, minus 24.
So whose rate is going to be the answer? Either A or C is answer. But the charge number?
Minus 12 plus 4.
So minus 8.
Yes, 82.
Fine. Solve next. Quickly, I suggest you. Okay, anyway, just solve it for the sake of solving. So if question will come from radioactivity, I believe you can solve. And also solve the question number 39 compulsory. That's very, very important. Question number 39. So how many questions done? Tell me. 38 is done. 36, 37, 38, 39. All done.
Yes, sir. 39.
Which one? Which one are solved?
39.
The rest is done, no? Are you solving directly 39 or you have solved 37, 38 also?
No, sir. I just solved 39. And 38.
So you solved 38, 37. No? Solve one question.
Oh.
Then come to 39. So once you're done with 39, let me know. I'll start the semi-conductor. Okay, so what is the answer for question number 48 without solving, just give me the answer?
So could
Tan
you repeat
is,
the question number?
pardon?
Please repeat the question number you just said.
48, 48, 48.
C.
Very good. Leave it. This time pass. Okay, solve 39.
Solving.
Just a second.
Sir, is it 5 liters?
That's correct. Very good.
Okay, so
And then solve question number 43. No, you start with 41. First solve 41 and then solve 43. So it will kind of take care of all types of questions that we have discussed. 41 and 43. Anyway, the amount of blood in human body is 5 liters, right? So it's a very
Yeah.
real life question. So I want these two questions must be solved. 54 also, which is based on the carbon beta. And then I think that is sufficient for today. The rest you can practice at home. Yeah. And then we'll just solve 55 by common sense. So 55 is a unique question. For that, you do not need any brain. In the 57. So this will have, these are like the different varieties of question that we have covered so far in theory. All right. So we'll start. So which question you're doing, guys? Tell me. Just which question you're solving?
43.
43. Very good. 41 is done.
Sir, yes, sir.
Very good. Just which question you're solving?
41.
21. 12.
Yes, sir.
Which question are you solving?
Yes, sir. I just completed that 30 is one, so I'm on 41 now.
So 39, you all got the answer 5.
Yes, sir.
Alright. So this was, I think this was also J advanced question. You can solve fast. You get the the whole idea. That see, every year, every type of question cannot be asked. So these are the variety of questions that you will come across. And the real challenge is the manipulation, not the concept. Even though you understand it, while writing it, you will find, okay, the numbers are not really good, how to manipulate and so on. All done? Forty-one, 43. 43 is over.
Yes, sir.
Very good.
Sir,
Yeah.
sir, the 55th question is about making out the first half of the graph, sir.
Just a minute. Yeah, I mean, just starting, like you have to think about which graph is more meaningful uh, in a decay process. See, the thing is, no one knows the graph unless you have seen it, on internet. So this is a
Yes.
question in which no one knows the answer. So we have to logically decide the answer. Okay.
Okay, sir.
So
Sir, so like according to the number of beta particles that's emitted, it will be like the same graph that we saw in today's class.
okay.
So
So
according to that, yes,
yeah,
sir.
yeah. So what's your answer? Which option you want to go with?
Sir, so the C option.
C is the right answer.
Okay, sir.
Because the logic is the fraction of energy. So losing nothing will have zero takers. And so losing all will also have the zero takers. So close to it, because the energy is very small. The energy spectrum of beta particle is from the radioactive source is this much. So there is a cutoff energy. I mean, it cannot emit more than E naught. And what is shown in the figure A, that it will reduce to E naught suddenly, like rapidly, which is not possible. So actually, this question having no answer, but you can only figure it out through logic. Okay, that this is more meaningful than this, the rest. So all done. I think only one is left. 57, you don't know. I think you want, I mean, if you know the formula. So I think I had given a formula for absorption, right? In X-ray, I think. Chapter. So
Okay, sir.
for any slab, if entering photon is I naught, what is the photon intensity leaving this? Mu is the absorption coefficient. What is the answer for I? Tell me, guys. I equals to? What was the relation? Tell me. No one remembers. So this is the relation. So once you cross a medium of thickness X, the intensity will reduce to this value. So using this relation, we have to find the solve the 57. Again, pretty easy. Just use it.
Okay, sir.
Okay, which question, guys? Tell me. That's which question is
57.
I'm doing 43rd.
43rd. 41 is done.
Yes, I tried it, but I answered in math, so I just went ahead right now. I'll try it.
It is 41. 41 is half-lives of two radioactive elements A and B are 20 minutes and 30 minutes, 40 minutes. Respectively, initially the samples have equal number of nuclei. After 80 minutes, the ratio of what is this? 41 is simple. You are saying 41 is done, no?
I answered in math, so I said I'll try it later, and I went ahead. I'll try it again now.
So A, B, 20, 40, 80 means how many T half? 4 T half? 2 T half?
Yes.
That's it, no? So the number of nucleus decayed will be how much? Delta M, 1 minus 2 power n, right? So delta M. Delta M is 10 dash. That's it. So what you can write, the number of decay will be how much? 1 minus 2 power 4. 1 2 power 2, right? Am I right, guys? Tell me yes or no.
Yes.
So
Yes,
how
sir.
much is 16? No? 15 by 16. 4 by 3. 5 by 4. No? Okay, this is
Yes.
not matching.
No, I went from the basic formula, so I didn't get this.
So basic will give you right answer only. Basic cannot give wrong answer, right?
Yeah.
So you have made your life unnecessary difficult, isn't it?
Yes.
See, finding the right formula to get the answer is also important. Like which case will have, or how fast you can do. See, everyone can do the way they want, but do it in a manner which can make it easy. Okay. All right. Solve 43. So 20 to 2 decays. How many do you have? 20, 10, 5. No, it's like T half is not good. You can go by the formula. So activity is given, right? It's the same formula. I mean, same question. Activity is given in the beginning, at the end. So the age. So you can directly get the answer. T equals to T half into log 2. How much? Oh, this is known answer, right? Log 210 is how much, guys? Tell me. I hope you know the answer. Log 10 base 2.
Sir, 10 by 3.
10 by 3. So 5730 into 10 by 3. This should be the answer. Roughly C answer, right?
Yes, sir.
One line question. Just a formula is given. What you're doing. Okay. Then solve 44. I think similar question, all are same questions. Yeah, just which question are you solving?
44th.
43, you got the answer?
Yes, I haven't checked it yet. Just a second. I'll check. Yes, correct. 43rd.
So what was your calculation that you got correct? Same?
Sir, we are given decays per minute, right?
Right.
And so we can directly use the formula, right? Like we are given that after some time it is becoming 2.
Hmm.
So what we can use is that 2 is equal to initially it was 20 e raised to minus lambda t, right? Hello.
Yeah, go ahead.
And lambda we can find by using the half-life.
Mhm. So you all are using something really weird, like unnecessarily making lengthy. Question which you can solve in 30 seconds, you're solving in 3 minutes or 4 minutes. So it means you're not learning anything. You're just using the same stuff, not trying to learn how to manipulate things. So this will not work. Anyway. So shall we start the semiconductor now? Or next lecture?
We can start now.
Start, sir.
Okay, so I'll just preface to the lecture. So what I'll do is I'll cancel this lecture. You can join in exactly 20 seconds after. So this is the end of the radioactivity. I'll start with the fresh recording.
Okay, so